All right, so our next example is a follow-up to the previous problem, adding in a complication of friction. The snowboarder begins at rest at the top of a slope, 67.2 meters long, at an angle of 23 degrees to the horizontal. This time, we can consider the coefficient of friction between the board and the snow to be 0.185. And we're once again asked, what is her velocity at the bottom of the slope? Again, we have solved this problem previously using Newton's second law to find the acceleration of the snowboarder, then using the kinematics equations to find her final velocity. But I want to show you now how we can use energy methods with friction to solve this problem. The setup for this problem is the same as it was in the previous problem. Step 1 is to draw a diagram of the situation showing the object at key points in its motion. Once again, we draw a diagram of the slope showing the skier at the top and the bottom. Right? We note that the angle of the incline is 23 degrees, that the length of the slope is 67.2 meters, and this time we can just put in that the height of the slope is going to be 26.26 meters. Step 2 is the same. Choose at what point in the motion we will have a zero gravitational potential energy. Once again, we choose it to be at the bottom of the slope to save us the problem of having negative numbers for gravitational potential energy. Step 3 is to note what the potential and kinetic energies are at the key points in the motion. So we note at the bottom and the top, nothing has changed in this case. What is different now is that we have a coefficient of kinetic friction of 0.185 for the slope. And that is going to complicate our next step. Step 4 is to use the principle of conservation of energy to find what you need to find. In this case, our conservation of energy equation is going to be a little bit more complicated than it was before because the work done by non-conservative forces is not going to be zero. Some things are still going to be zero, however. The initial kinetic energy is going to be zero, and the final potential energy is going to be zero. That much has not changed. But now we have to worry about the work done by non-conservative forces. Specifically, we have to worry about the work done by friction. So now we need to develop a formula for the work done by friction. Let's zoom in on the skier as she goes down the slope so that we can get an idea of the friction force acting on the skier. All right, so I'm going to draw the slope here. I'm going to draw the snowboarder here on the slope. Now, since the formula for work is work equals force times distance times the cosine of the angle between them, in that case, that's going to be the friction force, because the friction force is what's doing the work here, times the length of the slope d, times the cosine of the angle between them. Now, what's the angle going to be between the force and the distance? Well, we're still going to draw a force diagram. We never entirely get away from those, showing the forces which are acting on the snowboarder. We can almost always rely upon the weight force right there, mg. Since the snowboarder is on the sloped surface, the normal force felt by the snowboarder is also tilted. And then we have the friction force. Since the snowboarder is going down the slope, that friction force is going to be up the slope. Now, the motion of the snowboarder is going to be down the slope, and so this distance of 67.2 meters is indeed down the slope. The vector representing the snowboarder's displacement is in the opposite direction of the vector representing the friction force, and so the angle between them is 180 degrees. And the cosine of 180 is -1. So that takes us to this, minus FR times D, and we can rely upon the formula for the friction force, which is the coefficient of kinetic friction times the normal force times the distance. So now, in order to figure out the work done by friction, we've got to find out what the normal force is. We've done this before, previously, working with Newton's second law. And remember, when we did that, we broke up the weight force into components because we shifted our traditional x and y coordinate system so that the x-axis was down the slope and the y-axis was perpendicular to the slope. This means now that the normal force is in the y direction and the friction force is going to be in the negative x direction, and so we have to break up the weight force into components, wy and wx. Also remember, in our previous investigation, that we can consider this angle right here, the angle between the weight force and its y component, to be equal to the angle of the slope itself. So we can write out a formula for this y component of the weight force as mg cosine 23, since this y component is adjacent to the 23-degree angle. We can tell that the sum of the forces in the y direction is going to be 0 because the snowboarder does not rise up off the incline, nor does the snowboarder sink down into the incline. We have two y forces, the normal force, which is in the positive direction, and this mg cosine 23, which is in the negative y direction. The only way this can be true is if the normal force is equal to mg cosine 23. So just like we did when we were doing Newton's second law, we can come up with a formula for the normal force exerted by the slope on the snowboarder. So our final expression for the work done by friction is minus mu k mg cosine 23 times d. Don't forget to put this factor of d in there. That's very frequently forgotten. Taking this formula for the work done by friction, we now return to our conservation of energy formula. And now it looks like this. mgh minus mu k mg cosine 23 times d equals 1/2 mv final squared. Once again, the first thing we notice is that we do not need the mass of the snowboarder. The mass cancels out. We multiply both sides of the equation by 2, and we get 2gh minus 2 mu k g cosine 23 times d. These expressions can get fairly long, so you need to be very careful writing them out. Plugging in the values for our variables, we get that v final squared equals 290.4. That leaves us with a v final of 17.04 meters per second. Once again, this problem has 3 significant figures, and so we would report this as a final velocity of 17 meters per second.